She cut the curtain off, and she says, "Oh, you have enough hair for this." All right. So how are we doing? Any issues on the student side we need to discuss? I wanted to give you a little more help for the lab, so I think the timing's of the essence there. Time is of the essence since you have a deadline, so I'll do that first. And then I will talk a little bit about some of the thesis opportunities in the AI area that that concern that are kind of in my wheelhouse. I usually do that at the end of the course, but I know some of you are already thinking about this, so um, uh, it seems like we need to do it a little early. Okay, and then after that, tomorrow. We'll probably actually start we'll finish off. We probably can finish the neural network unit, and then reinforcement learning comes right after that. So, should give you some view of what we have, what's in store. I want to first actually just do a little bit more with the lecture slides. We're almost to the weight decay slide. It was like the next one. Okay, so here it is. So I'm going to leave the rest of the equations and stuff for tomorrow or the next day, probably tomorrow. But I just want to talk about this one because you already are involved with that through the lab. Okay, now again, the idea is weight decay is a generalization technique, and it's supposed to stop or help you control overfitting by constraining the magnitude of the weights in the neural network. Again, as if you do anything to you have your neural network, it has floating point numbers for the weights. If you do anything to say, well, these floating points are either hard out of bounds or are discouraged, that's going to limit the curves that the neural network is able to produce. It's less wiggly. It should be less able to overfit. That's kind of, short of doing a proof, that is what I can say about that. Now, the way the actual equation is really, really easy to understand, I think. So, I mean, because if I do this is the equation we know and love, right? Which says, update your weight for each weight, update your weight based on the partial derivative of the error with respect to that weight. You've been seeing that time and time again. Should be nothing new or scary there. So now we're just adding in a little bit. And what are we adding in? So this is saying when you update the weight, take the old value of the weight, the t-1 value, okay, multiply it by some constant, flip its sign, and also add that into your weight value at the same time. So if your weight is a big positive value, this means positive multiplied beta is usually positive. Okay, I've never seen anyone use negative. So sorry, I should probably say that. Beta is positive. Now we have a big positive. That means we're taking that weight and we're just chopping part of it off, right? So what's going to be left, beta is usually a fraction between 0 and 1. So if beta were a half, that basically, ignore this for the moment, that says, as part of the update, have the size of the weight. Okay, right? If it's a quarter, take off a quarter of the size of the weight. Now, if our weight is negative, it tells you to add a positive number the same way. So again, it's the magnitude of the weight that's being controlled. It's being pushed towards 0 constantly. every time you do a gradient update.
It seems like you cannot add momentum net at the same time.
Well, you might think that. But I'm going to leave momentum for another day. So there's a few slides in here. No, most those are two pretty common tricks, and yeah, they're kind of mixed and matched.
You have to stack multiple nets, like layers on top of each other, and you momentum some.
Well, let's leave that for the next lecture. I'm happy to try to grapple with any questions at that point. Just for everyone else's sanity to make them because I haven't even introduced momentum yet. So give me a little time. Okay, are we good on weight decay? So hopefully it's not just supposed to do something for gradual generalization, supposed to do something with the magnitude of the weights. Now you actually know what it does with the magnitude of the weights. Okay. Okay, so that was the first thing. Now, the next thing was I didn't really spend enough time, I thought, in retrospect, in the code. Again, this is not a lab where you must go in and do a ton with the code, but there's definitely some good stuff that can be learned there. PyTorch is not going away. We'll use it for the rest of the quarter. We'll use it all next summer. If you're doing a neural network, anything in your thesis, you're probably going to be using it. Maybe you won't be manipulating it directly. Maybe you'll be manipulating it via yet another library, but it'll still be there. So let me just take a little bit of time. And why doesn't it want to? All right, I want to make it a little more legible for y'all. All right, so okay, so let's just kind of scrape through this file. There's a second file, model.py, which I didn't say anything about. In fact, wasn't even listed in the manifest of files, but you have it and it's critical. That's the file that actually defines the neural network. So like if there was any in a normal neural network application where it's not all instrumented for you, that you'd be highly likely to need to open that file and mess with it, make things work well. Okay.
I was going to ask you about that. If we do the lab,
yeah,
can I mess with this file? And as long as I turn in at least one model that has one prelude fitting layer, can I add other layers?
Yeah, if you want to do it for comparison, it's going to do some extra work. Sure, that's very sensible, and you'll learn something. So I would encourage them. Sure. Yeah. But just like for the main grading for the class, or just to kind of make it a level playing field, everyone uses a one hidden layer network, at least for the one you're going to label best. But if you want to talk about some other ones and turn them in as well, sure. Awesome. Is everyone tracking that? All right. Good. All right. So this is your parsars, right? So you know about that. We demoed it yesterday. You've seen an invocation like this. It's doing it all in one fell swoop, where it's opening up the training file to be read as a binary file and doing pickle load. And that's the training data that we saw scrolling up on the screen yesterday. Okay. Now, so here's some of the good learning. I mean, so once you get down to the API, these aren't super deep points, but so PyTorch likes to do things a certain way. So it's different from what's intuitive to me. I like to have the data the way I created it, right? With the X's and Y's put together. PyTorch likes it to be separate, two different outputs. It's both fine. I don't like separate because to me that opens up the door for things to get out of sync. You have one extra one in one of those, in which case you just end up with a failure, or all the X's are now misaligned with the Y's are supposed to be with. That's what I worry about. But, in principle, if you're careful, it shouldn't make any difference. Okay? But since I have it my way, PyTorch wants it the other way. There's this function separate coordinates to pull the X's and the Y's apart. Okay, so it's just looking for every data point. Hopefully you saw yesterday it was an X comma a Y as a tuple. Okay, so it's saying for each one of those tuples, rip off the X and put it in the X's array, rip off the Y and put it in the Y's array and return it. And then they end up in X train and Y train down there. Okay. Well, the next thing you need to do is so if you haven't learned this already, for a very basic concept like a vector, like you would think that would be the one thing everyone could agree on because it's so simple. No one can agree exactly what a vector should look like. Everyone defines their own class. It's a little bit different from everybody else's. Okay. And PyTorch is no exception. So here we take our x's as a Python list and we convert it to a torch tensor. They call them tensors. Tensors just means it's not just a one-dimensional array or two-dimensional. It can be any number of dimensions. Emphasizing there. Okay. And then for some technical reasons, which I forget at the moment, it needs to be, so there's certain restrictions. It needs to have one more dimension than it naturally gets going through this process. I forget why that is. Is that maybe to compensate for the fact that our x's are just one dimensional? It might be, right? Because in general, there will be more than one dimension worth of values coming in. So, so maybe it says, okay, fine, you want to have one-dimensional data, that's fine, but then it needs to be a vector with one element, not just the floating point number. Okay, so that's this unsqueeze. There's also a function that does a squeeze, which does the opposite thing. It takes a dimension that isn't being used and removes it. Okay, and the index there, I think, just says, it just indicates where that is done. Okay, unsqueeze -1 would be, I guess, at the outermost layer. I'm not 100% sure, so I'd have to look that up myself to be 100% on that. But hopefully, at least get the idea. Shouldn't look like anything crazy or magic. That's my main concern. Okay. Now what we're going to do next is we reach into that model file and actually create our neural network. Okay, using an initializer, which is defined there. Okay, and we'll go look at that in a minute. The only thing it needs to know from us is the number of hidden units because everything else is locked down. Yeah, but there's only one included 7. Okay. You might be a little surprised how that looks in that file, but there's not a lot there, so you'll get over your surprise quick. The next thing you do is the loss function you're going to use is actually created as an object. Right? You wouldn't necessarily know that. That's just how Torch decided to do things. So in Torch, there's a neural network sublibrary, and in there's mean squared error loss as one of the options. Okay, and that's what we're picking. Says M is normally 4 mean, so it's a little redundant to have to say mean there, but I suppose you could do something like median or some other things in there or quartiles. I'm not really sure. Again, I'm just kind of following boilerplate here. You might be by the end of the course, if not at this moment, smarter than me about a lot of these details. These APIs, these libraries are big. Only if you make a concerted effort will you master the whole scope of it. Most of us just kind of use whatever we need, what's in our lane when we need it. And we need to relearn it, we relearn it. Okay. There's our learning rate. You know what that is coming in from the arguments. Here's my weight decay value that we were just talking about coming in over here. Okay. And then the optimizer we're going to use, you will know about other ones shortly, by the end of tomorrow. But this says Torch, it's got an optimization library. SGD is stochastic gradient descent. Okay. And then we need to pass it a bunch of stuff. So the model has an NNet object inside of it, which has parameters inside of it. That gets passed over. The learning rate gets passed over. The weight decay gets passed over. All right. All right. So that's all the setup. Here's the actual training. Okay. So again, we tell it, I want this many FX up, and FX is an entire pass through the data set. Okay. So for T in that range, here's what we're going to do. So we're going to reach in the model, get the neural net object, okay, give it, let's train T. Where was that?
You're going to pass X to it, and then you're going to look for what the model predicts Y. So Y predict is going to be the Y value that the model spits out associated with that specific X frame.
That's all right, but where is I didn't realize a big T had been okay. So a big T there is to indicate probably to me that it's the transpose. You know how you transpose a matrix, right? You basically just move all the elements across the diagonal. Again, it's one of those things where you kind of have to know what the API is going to want. It's like not a big deal to do it. If you don't realize that it wants it and you don't do it, you totally get the wrong answer. So it's one of those things you tend to stub your toes on unless you have a good guide to follow.
Is that specific to Torch or is it specific to the neural net?
It's specific to Torch. Yeah. All right. Now, the other thing you got to realize here is this, which you also might not necessarily expect. At one fell swoop, it takes all the X values and produces Ys for all of the Y values. Okay? Which is just kind of an interesting, for us right at this moment. But in fact, the fact that we can do things like this is what's responsible for the whole of modern AI. Right? And the fact that all the GPU sales that has made NVIDIA such a valuable company right now, okay? The fact that you can do this completely in parallel and producing one Y value has nothing to do with producing the next one, okay? That is an extraordinary fact, right? And we're not using GPUs here, but it's all set up. When you set things up like this, you're in a position where if you have a GPU and turn it on, which does not take much effort, you can now do things much, 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 much faster than you can with the CPU. So for us, with the CPU, it's going to do what you expect. It's just we didn't have to write the loop that says go through and for every X get the Y. So that's not much savings for us. But when a GPU is present, all of those X's will get farmed out to what could be hundreds or thousands of GPUs, and simultaneously they will all take their few X's. Now that what was a sea of X's has now become a little bit that's been assigned to each GPU, and they'll very quickly produce the appropriate Ys and send that back. And then the same stuff is done when you're going to do a gradient computation. The exact same thing is done, and that's a slide to the bottom. But yeah. All right. So here we produce. So we got our predictions. Now this just goes and takes the loss function and says, well, how are we doing? Okay. These are the values that we read in, which is what we would optimally like from the network. We know there's noise, so but that's what we're going to compare to. This is what actually came out of the neural net. This is going to go and hopefully compute the mean squared error because that's what we asked for. Okay. And here you see that every 100, starting with 0, starting with the initial pass, but every initial pass and every 100 after, it's going to print the loss. And yeah, so here's an interesting thing. So to get the dot item, what's that? Well, remember that PyTorch likes to do everything as tensors in its own format. And that sometimes is not convenient for printing to the screen. And if you were to leave off the item, I suspect you'd still be able to see the number on the screen, but probably say some icky stuff along with it, that it's this weird object and just some extra stuff that I didn't want to see. I wanted numbers I could just grab and put right into Excel, not ornamented with a bunch of extra stuff. All right. Let's see. For the backward pass, use the optimizer object to zero all the gradients for the variables that will update. Yeah, so the gradients are actually tend to be, I think at least notionally, they're kind of stored with the parameters, okay? And they're stored incrementally. Okay, so if we were doing something like a true gradient descent where we were computing the derivative over the entire set of data, then every time we passed it a new data point, it would produce a little piece of the gradient, and all those little pieces need to be summed to get the true gradient, and it would accumulate those inside the model. Okay, because it works like that as kind of an accumulator of values, it's important to zero it out before you start, lest the last thing you did with a gradient now influences the thing you're trying to do now. So that's what this is about. Okay. Here's the actual gradient getting computed. What you see? After all that setup, it's not, you just say compute the gradient. You should know how to do it, compute it. There you go. It's getting computed. And we're almost done. Then the very next thing is, okay, what are you going to do with the gradient? We're using stochastic gradient descent. That's what we said this optimizer should be. And it should take one step using the gradient. Boom, we're done. And then you loop. Okay, every time we loop, it's one complete epoch. Okay, the last thing at the bottom is just to dump create your modeled or your neural network on the disk so you can reload it later for your purposes. Okay, I think that's it. Any questions on this stuff? We're going to go look at the model file. Okay, the model file looks like this. Okay, it's just a normal Python object. Okay. The interesting part, so sometimes, so this does not have it. If this were a complicated or more sophisticated neural network, it would maybe have one more function there, which would be it's usually called forward, I believe, which doesn't just a normal forward path through the math to go from the inputs to the outputs of people. Okay. Since this is so simple, I guess I get along without it. You will notice that it's just an initializer, right? A creator for the object. It's a save and we'll, that's it. Okay. Now, the only interesting thing here really is what happens in the initializer. Again, when we created the model, we only told it one number, which was use this many hidden units. That's and hidden. Okay, I squirrel that away inside the object, and then I don't even think that's needed for this. Normally, I would do something like that because I'm expecting to have to write a forward function, and the forward function might need to know that, but we're not doing that there. So that's a waste. That could be done without. Okay. And then here's the actual neural net object, which you saw referenced, right? The model.nnet that you see in the train.py file is this object here. Okay. And now, yeah, so now some interesting PyTorch stuff. So PyTorch, has its own way of representing neural nets, okay? It is a layer-oriented API. So it always assumes that you're going to build your network layer by layer. And if you're doing that, one of the standard things you're going to want to do is you're going to say, well, for layers A, B, and C, they're like A first, then B, then C. That's the flow through the layers, right? There isn't a lot more to say. So the way you do that in PyTorch is you use this structure called a sequential, which is, to PyTorch, that's yet another layer type. But from my perspective, that's a container for layers. Okay, and then I need to give it my layers. Okay, now there's 3 things in there. It's maybe not what you would expect. Okay, so the way you represent a layer of ReLU neurons in PyTorch is as a linear layer. Okay, remember, no activation function or the identity function for activation function, followed by just the ReLU function. Okay, so what this says is I want a linear layer with one input and whatever my number of hidden units is, that many outputs. This doesn't need to know any numbers, okay, because it's just going to take however many inputs it gets. It's going to apply the ReLU function to each one and produce an output of the same dimensionality as the input. And then we're going to go through another linear layer to reduce the n signals coming in, one from each hidden unit, right? Multiply by weights, add a bias, okay, and produce one output, which is our function. Any questions about that? Okay, I hope that helps. It might anyway. And if nothing else, it's good background information because this stuff is always going to be there. It's only going to get more complicated than this. And they do a pretty decent job. Usually these files are not terrible, even for almost any application I've done. All right. All right. So I'm going to switch break next topic. Talk a little bit about what I do in my research, and you be the judge if it's of any interest to you. I know from talking to Matt that so even though you might not know who's going where yet, I guess it's going to be a while for you guys to figure that out. But 3 of you will end up in McWill, 1 will end up at MCU, and those are generally the people I end up working with in my research when well, as a general rule over time. That's certainly who I'm working with a lot for the last couple of years. So anyway, let me tell you what I do. So first of all, this tactical decision AI is kind of a made up term, but it's basically a AI that has to. I mean, I think it's appropriate. It has to make tactical decisions. It has to understand what's actually happening. It has to understand the situation and generate actions, whether it's for suggestions to a human user or more typically for my research, it actually takes those actions to be a player in a war game, for example. That it fits for both as far as I'm concerned. All right. So yeah, so the latest work we've done in this area has been motivated by some of the really impressive things that happened to AI over the past, 10 years. Um, like this champion level StarCraft player. So may have heard me say this before, but StarCraft is a game. It's definitely a game, but it looks a whole lot like constructive simulation structural. Down on the battlefield, there's a lot of war, there's all kinds of different platforms going on. Some are strong against one in one situation, some are strong in another situation. So the fact that the AI tech we have now is capable of building a StarCraft player that could be, it's like about 99.5% of all StarCraft players. That's pretty impressive to me. And yeah, my question is, where's our 99.5 percentile war game player or AI to drive units in a analytics simulation?
I remember I asked you this years ago, but did the StarCraft AI have the StarCraft has fog of war? You can see units that your units can see.
Yeah.
The AI also have that.
Yeah, no, it did.
So
it
you
did.
could only see what it was scout.
Yeah, it didn't cheat that way. Yeah,
Like how you
they try not to cheat at all. One of the biggest thing, the only way they had to kind of slow the computer down.
I'm about to say, did they reduce its APM?
Yes, yeah, they put a cap on that because otherwise, yeah. Otherwise, with really simple things that could do, which would be really hard for people to had to compensate against. But we'll read that paper in the summer, and because it's still an important example for a military AI. And there were some other games like Dota, if you know what that is, like a League of Legends kind of a thing. Board games like Go and whatever. So those things were happening at the same time. To me, championship level poker bats were also getting produced in that same time period, which because of the lack of knowledge of what's what's in your opponent's hand or what's in the deck, and the bluffing aspect, to me that was still less connected than StarCraft, but still pretty suggestive that we could do better for military AI. And yeah, I said this before to you guys, but yeah, don't play against an AI in poker for money. That's a really bad idea these days. Yeah, so the tech under the hood for these are both topics that we have not gotten yet in this class. That's why I usually do this at the end, but we're going to get to it, starting maybe this week or latest next week, starting with this one, reinforcement learning, but also game tree search. Well, we have talked about game tree search a little bit, but not the algorithms, which are, the best algorithms. We'll talk about those a little later. Okay. So the interest in DoD about this tech, I mean, it wasn't just me. A lot of people in simulation were pretty struck by these results. And here are the kinds of things that people think about. Hey, if I had this great AI, then for training, I wouldn't have to always have people training in a simulation against other people, right? But I could have a sparring partner, which would then be controllable, right?
I wrote a set of requirements asking for this and for a simulation. So you're actually spot on for what this is. One of the things that maybe isn't detailed here is the big thing people wanted was that the AI would be able to sort of move to meet players too. It wouldn't just stomp their neck in or whatever. It would say, okay, hey, you're progressing well, because that's currently something that is very specialized group of people who are having daily meetings to say, oh, they're this good, they're this good. And if you had an AI that could look back at a log of how people are doing and say, oh, they are choking at this point of the process, so let's take the pressure off them there and do that dynamically. It's setting these things up for training is really difficult, and as you were saying, it's like hundreds of people are currently expended on something that they.
Yeah. Well, you'll be real interested in reading the Alpha Star paper in the summer, because you will see that on their way to producing their 99.5%, their top player, they actually create a whole deep roster of players of varying abilities, which I'm not sure answers 100% of your requirement, but it answers some, because you can pull off the roster of worst players in a particular area without having to recreate a new AI. You just kind of get these other ones for free as a result of building the good one, the best one.
And you might be getting around to this, happy to wait on it. As far as, let's say, more real applications in a training simulation or something, not, I know what you're saying, the applicability of StarCraft, it has a lot of carryover to, if you can do StarCraft, you can do a much more military application, it's kind of what you're saying.
That's my sense.
No, I don't disagree.
Yeah.
So if we say that StarCraft, we hit 99.5.
Yeah.
Has anyone, I came from doing Gelictic for the Army. We didn't have a Gelictic AI that could do it at 2%.
Yeah.
You just could not turn it on and say, oh yeah, the AI is terrible, but you can do it.
Right.
It did not exist, period.
Yeah.
Is that, has anybody got a 10% AI for a?
Yeah, well, you'd have to answer that system by system, right? And then I know we're fighting that battle still there's plenty of systems that get delivered and are ready for use, meaning human versus human, and have no AI whatsoever. You just cannot. Not even an AI that will just pass its turn and let you just use it for a punching bag. You literally have to have the second person to be there to press the button and say pass if you wanted them to pass. So that's where we are right now. So we're still working through that as a department. Okay. Beyond that, so for operational planning, the thought was that if you have a superhuman AI, if you could get something in 99.5% or maybe even better, why not? Man, like in Go or in chess, those players are way above human level. You might not want those for sparring partners for a trainee, because the goal is not to pound them into the dirt. The goal is that they learn something, as just discussed here. But if I'm working on an operational plan, right, if it's as part of the decision-making process, I'm supposed to war game out in any serious environment for, again, it's the echelon and the time scale is going to have something to say about how serious the war gaming is. But if I've got time, you definitely want to war game things out. Would it not be good to have an AI always available there to run against your plan? It might just be as simple as, before I actually... So like how many times, even if you're very diligent, you're following the decision-making process by the letter, you will definitely war game it. In fact, you war game it multiple times, maybe to look at different COAs for your opponent. Okay, how many war games are you actually going to be able to do in any reasonable situation? War games are slow. People are not super fast. At most you're going to do a play or two or three, the idea here would be that the AI is always waiting for you. Overnight, when you first drafted the plan, you could first test it against the AI. Not again because the AI is going to behave doctrinally like your opponent, almost certainly not. But what you'd hope to get is that, okay, what if I just made a mistake, just a dumb mistake? Okay, rather than going in and then wasting the human wargamers play, it's like, okay, I set up the scenario wrong. I'm sorry, I wasted 2 hours of your time, right? Instead of that, you find the problem early, fix it before you go to the humans. Okay, that's the idea. And then, of course, in this whole in the whole area of analysis, simulations for analysis, which moves grads typically don't get into super with high frequency, but sometimes you guys have been in billets where you've needed to oversee analytic sims. So in an analytic sim, like all the battles will be code versus code. Okay. And the state of the art up till now is sad. It's just really sad. And the forces are basically on rails. Some human experts will go and say, okay, these guys are going to maneuver like this, and these guys will respond like that, which is, as a like as a going in as an ante, that's not terrible. Okay, but what happens if the contact elements by luck get completely destroyed? Right? There's no ability of the one side to replan on the fly or just do the obvious reflexive, okay, back up a little bit on that flank or anything. Okay. So my worry is this has got to be affecting the validity of what's coming out of those analytic studies. And I would like to see that fixed. Um, it's not all gravy putting AI, and it will make it will add extra complexity. There is a certain beauty of just running the forces into one another, and that the variability is very low then in what happens, and it's easier to see to do your analysis. But if it's not actually what forces do, what are you actually analyzing? You made it easy for yourself, but where's the value? Is there still the value there? I worry about that. Okay. So yeah, so the way well, I'll show you. You'll get a sense of what we don't have a lot of time. So I think you'll pick up a sense of how the flow is. But yeah, often students end up, helping figure out how, building AIs and or figuring out problems with the AIs and or trying to solve those problems, one or another or all of the above. Okay. So this has been if you're not aware, this has been a long thread of research in moves. We've worked on it for, coming up on 15 years, but really intensively in the past 6 years or so. And so we've got a good path. So we've got a lot of experience getting students through for these types of topics. We've worked with a lot of different partners in the Navy, and of course, still have good contact with the Marine Corps, mostly through your peers that are off in those billets that I just mentioned. And we've worked almost continuously with track downstairs and quite often with DevCom. And I don't know. I think they seem to be getting closer and closer. I guess there's some organizational changes in the works there. And yeah, ONR for sure is funding my work this year. I'm not sure about DevCon. They said they were going to, hasn't happened yet. We'll see. So um okay, so just to give you an idea, and I'm glad I have this here because we didn't go through reinforcement learning yet. So in reinforcement learning, what you have is you have a neural net that either directly or slightly indirectly specifies a policy for its units, which is what it's going to do in any given situation. And to start with, neural nets, the weights for neural nets are randomized. Okay. And so the situation is like what you see over here. You see these red guys. That's a random neural net for them. So the red only improves their score, gets a reward in the sense of reinforcement learning by killing blue. But he doesn't know that. They don't know what they're there for, They can't read my mind. Until they kill the first blue guy, they don't get any reward. So that's why, they're in no particular hurry. I mean, they just see there's nothing special about those blue guys. The combat happens automatically. That's the first time a red guy killed a blue guy, more or less by accident, and they got a reward for that. Okay. So that should encourage them to realize that, oh, maybe going up toward the blue guys is a good idea. And this is a slow process. So this is trial and error learning is what reinforcement learning is. And you can learn almost anything by trial and error learning, but that's not to say it's fast. Okay. What makes it practical is computers can run fast and they can be very big. Okay. And if you look at this thing, you'll see after a while, then the behavior never gets wonderful. That was one of our first things we did. We created that like 6 years ago. Yeah. So after an hour of training, which is not much, normally ones we build these days take a day or two or a week to train. It seems to know what it's doing. It does understand it's there to kill the blue guys. All right. So stop that. And then just to show some other things. So wait for you. Yeah, so here we've got so often we're trying to build AIs for them from the red perspective, right? Because the blue is they're going to be the trainee or something like that, or the analyst. So here we have red in the attack, right? Three companies, a company and a platoon of blue. And this was a study that showed that reinforcement learning has the capability of finding optimal solutions for both high and low urgency situations, which you'll understand a little better when we actually start talking about it. There is a parameter, it's called the discount factor, but doesn't have to do with shopping. So the discount factor actually allows you to do this. So you can see in low urgency. So in other words, if it's red's job to kill blue, but it's low urgency, what should they do, right? So in this case, it's not just killing blue that's good. They also want to do force preservation. So they learn that, okay, the thing to do is just everyone group up on one guy and then kill the other guy at our leisure, right? Yeah, that's the right solution. Now you'll notice like there's some oddities here. You may notice that when they go over to get the platoon, like one red guy doesn't follow. Why is that? Well, because of the length of the simulation, it was such, and because the other two guys are in his way, he couldn't actually get into the fight. So he learns that. So he just sits there because he knows he's not going to be able to do anything good. Okay, then down here is kind of the high urgency situation. So now it's like, yeah, we do want to kill blue, but don't take forever about it. And now you see what you'd expect that red splits off one company right away to go after the platoon. And yes, red's casualties are slightly higher. In that circumstance, what would you expect? Okay. Yeah, so we've done a lot of stuff with this. So that was very early work. Lately, so I built this at-level thing, which you guys saw in the summer, which we still use for the summer course, and it's still used for thesis work, and it's been used a bunch of places now. It's been used across the country for various projects, here and there, not massively used, but some maybe a little hard to see, and some it's pretty easy to fine tune. So this is some work some of your forebears did for the wargaming class. They built an adjudicator using Atlatl for island warfare. So it was part of a bigger war game. And when a conflict happened on an island, then they would split out and they would go into this, and they had AIs playing both sides to say what happened. Oh, blue won, but he took 10% casualties. Okay, and then that's injected back into the war game. The war game continues. Yeah. So, but this is not, so this is just it. I mean, it's good for what I built it for, which is for research and for teaching. So it's not being getting serious use. Even when other people are using it, they're using it for some have been students at CMU or other places. Some have been other military research labs that were trying to do research. They weren't doing, studies that were serious studies.
For reinforcement,
Yeah.
we had a guest speaker a couple of quarters ago who was talking about reinforcement learning in the context of a taxi game. You had 500 states of basis was very small.
Yeah.
And gave me the impression that reinforcement learning meant that the engine would be able to, given a state and a known goal state, obviously with perfect information about the entire state of the board, would be able to do some math on each state to determine exactly which the correct next step for its person to take. So it can figure out a way to get to the goal state without having to go randomly across different directions. Although I recognize that math that it's doing because it's cascading is essentially it's doing math.
I mean, it's doing math because it's a computer, so no arguments with you there. But yeah, so it's not a technique though that just uses the basic principles of I understand the state, I understand how the state advances over time, and then only doing math. What would the neural net be for in that case? But what it's doing is it's using a neural net to go and say, well, in this situation, based on prior experience, these actions are the good ones. So let's do those. And then if it's wrong, it learns that over time, and eventually, it can approach optimal behavior. All right, so I'm gonna leave this on the side. Bigger scenarios, blah blah blah. Enable scenarios. Um, there's yeah, there's a lot of possibilities for interesting stuff in this area, but I just wanted to show I have 5 minutes, so I just want to show you some of the things that the Marine Corps has been putting in front of me these days. Um, so this game, Command P, is the one that is being used for the war game that NPS runs. Okay, they're not heavily leaning into the tech and the AI possibilities with Command PE, but it is supposedly the choice for doing Marine Corps wargaming in the near term. I'd be willing to take a look at that. I have not done much with it other than play it as a player. Um, but there's been some impressive results from an industry partner that came in and did a demonstration called Project Endgame at Quantico like a year ago. It's a very mature product. It's been around for a while. There's a consumer version, so anybody can go pick it up for 50, $100, whatever it is. You won't have everything that's in the professional edition, but you'll have a lot. So yeah, it's something that I would be willing to dig into at the right moment. If I really knew there's a payoff there for Marine Corps wargaming, which there might be either now or soon. Um, so this is another platform the Marine Corps is interested in. So this one is not for wargaming as much as for PME, being used by Marine Corps University, but they seem to really like this game. And the code is in pretty decent shape. So I've spent quite a number of hours playing with it. It's not perfect. I'm asking for some changes, but I think it's hopefully will get better soon. I do have one student that's looking at this already, a Navy CS student, but this is just a platform. It's not a thesis, right? So you go and you define, say I'm interested in this aspect and I'm going to explore it in this other way. So that doesn't have to limit you guys. That there's some student looking at this. This is tactical scale, ground-centric warfare. And some of the scenarios are very UAV heavy, which was a problem for me. I didn't know how to employ them right, but Nick did well. So this is up there. If you're on the Marine Corps Wargaming Cloud, you can this product is there. And it actually has some innate AI, but what it hasn't had up till now is the ability to let third parties come in with an AI. So the Marine Corps could say, well, we want an AI that does whatever, this or that, or does just plain does better than the existing AI. But that interface is now coming into existence, and I think the timing is right. We can do more with it. Okay, this game in the image behind is called this Assassin's Mace. The wargaming system is called the Operational Wargaming System. This is like a Marine Corps product, front to back. So it was then Colonel Timothy Barrick who defined that system. He's later retired, but he's a wargaming director for MCU now, so he's still very much around. And it was a big, messy game like this, operational scale, but the intent was to be able to do, all of Ukraine scenario, or as in this case, East China, all the East China Sea. I mean, everything from Guam up to, deep into China, where it could be missile launches or what have you. So this has now been digitized. The interface really hasn't been used for much. So all these projects have come with some degree of risk because it's like brand new code. Even when it looks good, kind of have to expect you're going to have some issues, but it looks pretty good. The guy the main coding of this was with Unity, like you guys. Unity's an exporter for you guys, right?
Of Unity.
You know of Unity. Okay. Well, this is the Unity engine. It's created at NIWC out in Hawaii. So they actually built this. The AI interface was built by a contractor, but he's quite good. And we're just setting up to give him some more resources. They're going to run through September. So the timing isn't awesome. for you guys, but I'm hoping to get the AI interface to kick it a bit more, kick the tires and maybe get between myself and any of you, or maybe in the summer course, whoever has time to go and torture it a little bit and try to find the problems earlier while the developer's still around, while he's still under contract, and we can ask him to do stuff for us. He's quite nice to work with, though. Okay, and last but not least is this thing. Uh, Actually, this is two projects, but they're from the same company. The company's called Code Metal. Now so the current plan, so you guys maybe you're more aware than me, but also maybe not. Like, the plan that for what products will be used for Marine Corps wargaming has really been thrashing over the past year and change. There was a thing called Pioneer, but Marine Corps wasn't happy, so that got cut. That's not a thing anymore. As I said, Command PE now seems to be like the near-term plan because that's a product you can pull from the shelf. So I think, maybe Neller Center should already be functioning, right? So I don't know what they would have to use besides Command PE. There probably are other things I don't know about, but that's what I know about. So like that's the plan for today, up to maybe a year out or like 18 months from now. And then the plan I was shown shows them switching to this war engine from Code Metal. So this is something that's being coded right now. They're doing a first demonstration of a war game this month. I was just on a telecom with them an hour ago. I know they're working hard on it. It's not just the Marine Corps. It actually started with Air Force money, but the Marine Corps now has signed on as like an official partner. And I was told we're in February, Marine Corps would get initial code dump, so we could start maybe taking a look at it. So I got a sneak peek of some products by that company because they also have this thing called Wargaming for All, which the Air Force is paying for, not the Marine Corps. But the idea was to have an open AI competition at the unclass level and to get students from specifically MIT and Stanford, but also other places to go and compete to see who could build the best AI. Now, to be honest, it's been a bit shambolic, the whole thing, the Wargaming for All part of it. Maybe because I hope because they've been focusing more on the war engine, which is kind of supposed to be a serious Air Force / Marine Corps wargaming product. But I don't know. But some things I like, even though the organization hasn't really been there for this, I was able to look at that code. It's got a fast C++ kernel. I couldn't see the source, but it is very fast. I could verify that. It's got a Python interface, which, that's what you like to see these days. It makes it easy to interact with the kernel. Yeah, so we'll see. So I'm continuing to watch Wargaming for All. I wouldn't mind actually using that for something at NPS if they will get their act together. And if they don't, I don't want to waste student time on it. And again, they said this month for a demo for War Engines, but we'll see. Okay. And I'm past my time, so let's stop there.